Yes, hello. Unfortunately, I couldn't be there in person today, but I will present the results of two of my PhD chapters on monk parakeet vocal culture. First, I would like to thank my two supervisors, Mara Brooke McElrath and Lucy Eplin, for giving me the opportunity to work on this. Then the two collaborators on these papers, Stephen Tyndall and Juan Carlos Senar. And finally, our local field assistants, Andres Manza, and of course, the funding agents. First, I will present some general background on vocal culture and the study species, and then the results of our dialect study and our study of the vocal signature at the individual level. So first, why would you study language in other species or vocalizations in other species? Language is a hallmark of human cumulative cultural evolution, and is a very complex trait to learn, especially if you live in a country such as Denmark. It's also a very complex trait to evolve, but luckily it exists at a much more rudimentary form in other species that also have vocal communication. If you assume that vocalizations are socially learned, and these are socially learned in a lot of species, you would expect dialects to form. This can either be through passive processes or active processes. Two of the passive processes are the founder effect, where a small group will migrate and found a new population, and then new individuals can only learn the vocalizations from the original founders. Or you can have cultural drift, where an isolated population slowly drifts away from the species norm. The active processes, you have conformity, where a group will conform on how to perform certain vocalizations or which vocalizations to learn. And they can even develop kind of a password where group members have to learn a specific vocalization to be accepted in the group. You can also have the opposite going on, where individuals try to sound as distinct as possible from other individuals, and thereby filling up the entire acoustic space. This would, of course, obscure any dialects, because now all groups will fill up the entire acoustic space. But this has some clear advantages for the individual, which is the second part of this presentation. Early work on this was done on shorebirds, where returning birds would vocalize and their mates would recognize this one vocalizing individual among hundreds of other vocalizing birds. A lot of work has also been done in primates, where it has been shown that you can recognize an individual in multiple call types, and that the level of individuality differs between call types. But so far, nothing has been done in a cross-call type signal in a flexible vocal learner. So humans can learn to produce new vocalizations their entire life, but you can recognize the speaker no matter what we are saying and how we are saying it. So we propose to study parrots, which are also flexible vocal learners. They can learn to produce new vocalizations their entire life, and they have a very large and flexible repertoire. So we want to know if there is this cross-call type signal, and we want to know how the individual signal in their main call type, the contact call, develops over time. So the contact call is a call they use to broadcast identity, kind of a name for themselves. But first, we studied dialects in the European invasive range, and for this we studied the monk parakeet, which is a small gray and green parrot that lives as an invasive species in a lot of European cities. Their parents will build a new stick nest on top of an already existing nesting structure. So each black dot here is a nest entry into a nest chamber, and multiple pairs live together in these complex nests. They produce a lot of vocalizations, and together with Stephen Tyndall, a fellow PhD student, I recorded these with the directional microphone and recorded which individual was vocalizing using a camcorder. Important to notice is that these individuals are not individually marked, so we couldn't know if we were re-recording the same individual in a later recording. We recorded monk parakeets in 8 cities throughout Europe of varying population sizes, and if possible, also recorded multiple parks per city. This is how they sound when they sit in their nest. So basically, they're just squeaking a lot, but they also produce growls and whistles. For the dialect study, we are mainly interested in their slightly longer squeak, which is their contact call, which you can see over here with frequency on the y-axis and time on the x-axis. These calls are only a fifth of a second long, so they're really short, but they have a lot of frequency modulation going on. The frequency is going up and down and up and down. This is just so fast that we can't hear it, and we just hear this single squeak. To look at dialects, we first sorted these into several variants, and then plotted how many of the calls fell into each variant per city. Over here, you can see in orange the largest proportion of calls in that city. So in Brussels, they mainly produce this mixed alarm call, which is variant D over here. And in Pavia, this was the only city where they produced this B variant with the 4 very stereotyped triangles. We also quantified this more continuously, where we traced the fundamental frequency, so the lowest red line here, and then pairwise compared these traces across calls. From this distance matrix, we created a 2-dimensional space using principal coordinate analysis. And over here, you can see dots represent calls, and they are colored by city. Then to quantify city level differences and park level differences, we used the multi-level Bayesian model. Over here, you can see in bold the city level averages and in thin the park level averages. So from this, it's clear that there are city level differences. For example, Barcelona and Brussels are very different. And you can also see that Brussels, which has this very weird mixed alarm kind of contact call, stands out from most of the other cities. You can also see that there are some parks that stand out from other parks in their city, but this signal is much less strong. And now it becomes important to remember that we couldn't individually mark these birds, so we didn't know if we were re-recording the same individual multiple times in a park. To test the effect of this incorrect pooling, we used a sensitivity analysis and showed that the park level differences could be a spurious result, but that the city level differences were so strong that this couldn't happen even under the most extreme case of incorrect pooling. From this, we concluded that there either has been a founder effect with a small captive population escaping and starting a focal culture in a city, or there has been drift going on because these cities are very isolated. Individuals do not migrate between them. We also concluded that it's unlikely that monk parakeets converged on a group signature within parks, because then we would have expected a much stronger signal of park. And finally, we couldn't say much about the individual signal because we couldn't re-record individuals. So for that, I went back to Barcelona, to Ciutadella Park, where our local collaborator, Juan Carlos Sinar, has done an amazing job and tagged thousands of these monk parakeets. He caught them and then put these small dog collars around their neck so that we can recognize them easily from the ground. I recorded vocalizations of several hundreds of these monk parakeets over 2 times a month across 2 years, and then sorted these vocalizations into different categories. I don't have time to go into all of them, so I will focus on the contact call, which is the squiggly call up here. We again pairwise compared these using cross-correlation, and at the point of maximum overlap computed the acoustic distance, so dij. Then we used 3 models to model this acoustic distance. The first model focused on the effect of individual and of recording. You can see the results over here, where the more to the right a density is, the stronger the effect, and the gray dashed line is no effect. In green, you can see the effect of individual, so calls coming from the same individual sound more similar than calls coming from 2 different individuals. But in blue, you can see the additional effect of recording, so calls coming from the same individual within the same recording are much more similar than calls coming from the same individual but across recordings. So they're very variable between recordings. Next, we wanted to know how quickly this variability increased. So that's the second model here, and the blue line up here, which models acoustic distance between any 2 calls as a function of the time separating them within a recording. And from this, you can see that calls only 10 seconds apart, which is up here, are already much less similar, so the acoustic distance is greater than calls that come from within the same second. So this variability really rapidly increases. And then finally, you can see over here that the acoustic distance does not increase over days. So the last model models the acoustic distance as a function of the days separating the recordings from which the calls came. And calls coming from the same day are just as similar as calls coming from recordings 30 days apart. Then finally, we wanted to know if there is some cross-call type signal. So can they recognize an individual no matter what vocalization they are using? For this, we sorted the recordings into a training set and a testing set. From the training set, we used all the growly calls, and from the testing set, we used all the tonal calls. Then we trained an LDA to predict the caller ID and tested the performance on the testing set. We also trained an LDA where we switched all the labels of the caller so that it couldn't learn any features, and then compared the performance of these two models. D here is the main result. I don't have time to go into all the details of the other results. And you can see that the trained LDA on average classified 24% correct, and the random LDA only 9%. To see how stable this result is, we permuted this 100 times. And over here, you can see the density of the differences. So on average, the trained LDA was 15% better than the random, and there was hardly any overlap with zero, meaning that there is some feature that the trained LDA could learn to outperform the random one. And as far as I know, this is the first evidence of cross-call type, vocal voice print, you could call it, in a flexible vocal learner that's not a human. And with that, we have come to the end of my talk, and I'm happy to take any questions. And if there isn't time, then please reach out to me after.